This video will cover running a 3D code using the 21 by 21 by 21 pipe that we created. So we need to edit the params.in file. And we need to change the LX to 21, and the same for the LY and LZ. The characteristic length is going to be on the order of 21 minus 2 is 19 for the diameter of the pipe. For the moment, we'll stick with these small frame rate and small number of frames. We'll stick with tau 0 equals 1. But we will use a driving force. I believe our pipe is oriented in the Z direction right now, so let's put a driving force in the positive Z direction. That's a gravitational acceleration. And basically, none of the rest of this will be an issue at the moment. We'll turn off all the pressure boundaries. And that should really take care of everything. So let's try to first make, and I guess by rights we should have checked the flags file, but I think we might be safe to assume that it's set for a single component at the moment. And now let's try to execute. Apparently it's not set for a single component. So this gives us an opportunity to go back to the flag. Well, it's set for a single component, but with a different option for a macroscopic porous media set. Single fluid component. And let's turn this porous media off. And since we're here, we'll look at the rest. Non-local forces are off. This is for multi-phase simulations. And none of the rest of this is really relevant to us right now. Let's save it. Of course, every time the flags file is modified, we need to recompile. So we'll execute make again. And now we should be able to execute the program. It's running very quickly for this small domain. We can see there's a velocity only in the Z direction, and the maximum is reached about 0.8. That is not stable yet. The previous time said it was 0.07. So now we will go back and modify our params.in file so the program runs for a longer time. Perhaps 10 frames is still good, but let's choose 1,000 times steps per frame. And we should readily, I think we will achieve equilibrium under these circumstances. After just a minute or so, we have the results. Let me point out first that the minimum density is, approximately 1 to 3 decimal places. The maximum density is 1 to 3 decimal places, and the average density is 1 also. The minimum velocities are here in the x, y, and z directions, and the maximum velocities are here. This is a relatively large maximum velocity, a bit higher than we would normally like to use. And this is the average velocity. So for a first comparison, let's see what those values are expected to be theoretically. So looking at the results, we have a pipe radius of the diameter divided by 2 is 9.5 lattice units. We set the gravitational acceleration at 10 to the minus 3 lattice units per time step squared. Viscosity was determined by the tau 0 value, which was set at 1, leading to a kinematic viscosity nu of 1/6 lattice unit per time step, or lattice unit squared per time step. And our formula for the velocity as a function of distance r from the center for a radius of a is the gravitational acceleration times divided by 4 times the kinematic viscosity. And so the result we get here for the theoretical value is about 0.135 lattice units per time step for the maximum velocity. And if we look at the simulation, it was 0.1295, or roughly 0.13. Again, not bad for a very small pipe. For the case of the pipe, the average velocity should be half of this computed maximum, or 0.0676. And if we look back here, we got 0.06, sorry, that's the minimum, 0.0637.